Okay, so now we continue course with discussing neutrons, how neutrons interact with materials. Well, first of all, neutrons are of course neutral particles, so they don't interact with the electromagnetic force, and because of that, the main mechanism by which they interact with materials is by the nuclear forces with the atomic nuclei. And the nuclei, as you probably remember from your physics studies, are very small, of the order of femtometers, so this means that the collision probability is quite small. And this is the basic reason why neutrons travel quite far in the matter. Well, getting more detailed, how do the neutrons interact with the materials? There are many ways in which they can, and one can maybe argue that these 5 listed here are the most important one. Although a neutronic specialist might disagree, but this is what Gary Wassey's book lists as the most important one. In general, there is a big field of neutronics which uses computer codes to model neutron passage in materials, which is very important, especially for understanding and optimizing the operation of fission reactors. Well, on this course, we don't intend to make this a neutronics course, but we'll just mention briefly what kind of interaction mechanisms these are, and hence what are the mechanisms by which the damage is eventually produced. Well, the simplest one is elastic neutron scattering, and this is going again back to first-year university physics, the collision of two spheres, which actually has a pretty good approximation in neutronics, can be considered two hard spheres. So one can use the classical kinematics equations to deal with these, and actually the basic equations are the same as for electrons, because electrons, of course, at high energies also can be considered a classical particle. So this calculation gives equations where this energy transfer T is given by this equation, where the gamma factor is the same as we had earlier for the classical treatment of electrons. And here you see that it's proportional to the initial energy of the neutron mass, and then proportional to or depends on the masses of the neutron, small m, and the nucleus, big M, according to this equation. And this will have an angular dependence of the shape shown here. Here again, the maximum is a direct head-on collision, which means the neutron would scatter backwards. Well, if one calculates an average of this, one can get typical energies of what this can mean, and this is something which starts to relate to damage production. So you take a 1 MeV megaelectrovolt neutron carbon, you get an energy transfer of 0.14 MeV, so 140 keV, and going up in mass to uranium, you then get 9 keV. So the atomic recoil energy is actually not in the MeV range, but in the keV range after neutron collisions. Of course, if the neutron energy is higher, then we'll get higher values for this energy transfer as well. Well, at high neutron energies, one can also start getting inelastic neutron scattering, which means that something happens inside the nucleus, that is, the nucleus can be excited, and in this case, the momentum of energy does not need to be preserved in a two-body collision picture, and one cannot actually give any simple equation for what the energy transfer is. Well, at even higher energies, more exotic nuclear reactions come in. There are several reactions where a neutron hits a nucleus and then something comes out. And one of them, maybe the simplest one, is an N2N reaction where one neutron comes in and two neutrons get out of the collision. And then there is the class of N-gamma reactions, and these are important for thermal neutron energies. What this means is that a nucleus absorbs a neutron and releases a photon, a gamma particle, of course, because we are dealing with nuclear physics processes. And this gamma particle usually has MeV energies. And in this case, one doesn't directly get a heavy recoil energy if the neutron energy is low, but the emission of the gamma then gives a recoil to this new nucleus, because photons have momentum according to the energy over divided by c. So then one gets this momentum is transferred to the nucleus, and it turns out that the recoil energy is a few hundred electronvolts. This is of course much less than the keV energies mentioned for the elastic collisions, but even a few hundred electronvolts is enough for damage production. We will return to this damage production mechanism later on during this course. Well, the fifth process I'd like to list here is nuclear fission. And this is, of course, the very basis of why fission reactors work in the first place. And this is definitely familiar to you from your previous physics studies. So nuclear fission, nucleus is hit by a neutron, which can be either thermal or high energy, but in a fission process, the big nucleus splits into several smaller nuclei. And for this, then all of these particles emitted after the fission reactor can produce damage. The neutrons still likely have high energy, so they can produce damage as the new MeV neutrons described earlier. But most importantly, the fission products actually typically have very high energies, hundreds of mega electronvolts. And this is quite a lot of energy, and this makes them produce damage by hundreds of mega electronvolts particle damage production mechanism. And this is known as the Swift heavy ion regime for damage production, producing what's also known as fission tracks. We will describe these Swift heavy ions and fission tracks first in this end of this section in subsection 2.8 and later on during the course in some additional detail. What is important to know that this here is there is a big variety of what comes out and a big variety of the energies. This here is an very old data of the energy distribution of the particles coming out from either slow neutrons or spontaneous fission of plutonium from the 1950s. And in general, most fission reactions have a wide energy spectrum and wide mass spectrum of the fission products coming out. So that was the very basics. As I said, it is possible, known to most of the nuclear reactions up to maybe an energy of 10 or 20 MeV are well known, have been tabulated. Some of them are very complicated in energy dependence, but they have been tabulated, and there are softwares which allow calculating, in principle, all neutron reactions with a material. There is no way we can start going into details, but let me just tell that this can be done and has been done for typical reactor relevant situation. This graph here illustrates a distribution in the neutron flux as a function of neutron energy in a fusion environment. The blue curve, the demo is supposed to be the first fusion power plant. It doesn't exist yet, so this is from a demo design study. And then on the other hand, the black curve is in a regular fission pressure water reactor, a regular fission reactor which do exist. And what is noteworthy here at the neutron spectrum is quite different, especially in fusion. You have this very strong peak at 14 mega electronvolts, which comes from the deuterium-tritium fusion reactor. And this peak, although it's narrow, you see it's an order of magnitude stronger than more, so it has a very prominent role in the damage production in fusion environments. Whereas in fission you see that most of the damage is produced by mega electrovolt neutrons, but there is also a low energy tail, which actually can also be important for damage production, depending on which part of a fission reactor one is. Okay, and the last part of this section is a first overview of the damage production by ions. And this I say first overview because later on we have a full section devoted to this, or actually in a way 2 full sections devoted to this topic. I'll motivate in a moment why we put so much emphasis on damage by ions or atoms. But to start with, there are 3 different main mechanisms. One is collisions with nuclei, atom cores. Another one is collisions with electrons, which can occur with several different mechanisms. And finally, there is damage by nuclear reactions and also by Cherenkov radiation at high energies. And at high energies, this means hundreds of mega electrovolts or higher. So, first of all, these ion-nucleus collisions at high energies, they are classical binary collisions under a Coulomb repulsive potential, and at lower energies, they are screened. And the next section will deal with these classical binary collisions in quite some detail. Well, but it can also collide with electrons. Ions are per definition charged, so they can collide with electrons. But because the electron is so much lighter than the ion, the collisions with electrons do not really change the direction of the ion appreciably, except at very low energies, maybe a little bit. The nuclear reactions can be very complicated, but most of the time they are not really significant for damage production for ion implantation and neutron irradiation kind of situations, so we don't deal with them in more detail. So, the ion-atom collisions can once again be calculated with these same classical binary collisions. One gets this equation, which by now should be already familiar to you. So you have 4 times the ion mass times the atom mass divided by the ion mass plus the atom mass squared. This multiplies by the ion gives the maximum energy an atom can receive. And this is again the head-on collision energy, so this is true only if the collision is right head-on. If it's at smaller angles, there is a scattering which transfers less energy. And this will all be calculated and shown how this can be calculated in the next section of the course. This was the classical equation. Of course, in principle, there is the relativistic version, but mainly it's needed for protons who may start approaching the speed of light. So what happens when an ion enters the material? Well, roughly speaking, when it enters the material, it may collide at any point, but in the beginning the collision cross-section is small, and then it mostly travels in a straight path. Here it does collide with electrons, so it loses energy to electrons, but mostly it goes in a straight path till it has lost enough energy. Then the collisions with nuclei start dominating and one gets a more complicated part. And this can be schematically illustrated that initially you have collisions with electrons, then collisions with nuclei. This is true if the initial energy is high, say hundreds of keV or higher. If the initial energy is low, then one is immediately in this situation, as we shall also see later during the course. So that was a schematic. Here is an illustration of how this can look. So this is a molecular dynamics simulation. There will be many of these simulations during this course. But the point is that in this simulation, each dot is an atom, in this case a gold atom, and this is 30 keV xenon impacting on the gold, and we'll see what happens here. This plot also shows the maximum energy of the system, which initially is the energy of this 30 keV xenon ion, which will hit the gold. Now we see the ion enters the material, first indeed travels straight, but then starts colliding more. One gets a sequence of collisions, but you do notice that there is also some collisions close to the surface. you get actually a very complicated behavior, lots of damage for a moment, but in the end almost all damage regenerates. Now you don't have to worry if you don't understand everything in this picture yet, because we will go through in great detail everything that happens in this picture, including what these final damage structures are. So you will during the course learn what exactly was going on here. So at this stage this is just a first illustration of ion impacts. Well, then there are the electrons, as I said, the electrons slow down the ion. There are much more electrons than nuclei in any material except hydrogen. And the electrons are smaller, so to a very good approximation one can treat the electrons as being an average frictional force which slows down the ion. This force is known as the electronic stopping power. And this is a very important terminology, this stopping power, so we'll deal with it, discuss it also in detail. Well, the collisions with ions, they can also be averaged in the same conceptual way, and then you can talk about nuclear stopping power. And finally, the nuclear reactions can be averaged and considered a nuclear reaction stopping power. And typically, the energy dependence of these terms looks something like this. So we have the total stopping power is the sum of the nuclear, electronic, and nuclear reaction part. And but thus plots this on a log-log plot, logarithm of energy versus logarithm of stopping power. One gets at low energies, one gets the nuclear stopping power dominates for all materials except protons. Then going to higher energies, the electronic stopping power always dominates up to an energy of maybe 100 keV per AMU. This AMU, atomic mass unit, signifies to the mass of the ion coming in. And finally, the reactions start coming in at very high energies from the, roughly speaking, hundreds of mega electrovolts up. This is the beginning of this discussion on stopping power. We will also discuss the electronic stopping power in much more detail later on. At this stage, it may be good to already now tell an important terminology point that especially in detector physics and space physics, the electronic stopping power is known as the linear energy transfer let. And this is a little bit confusing because sometimes let is used for the total stopping power. Typically people who do this are people dealing with high MeV or gigaelectron GeV energies, because at these high energies usually the electronic stopping power completely dominates, and then one can say that the electronic stopping power is the same as for practical purposes, the same as the total stopping power. Then there is another term, non-ionizing energy loss, which is which essentially means the nuclear stopping power. So it's quite unfortunate that there is this terminology confusion, but on this course we will be almost exclusively using the terms nuclear and electronic stopping power. But if you run across these terms, you now know that they are essentially the same. Let is essentially same as electronic stopping power, and nil is essentially the same as nuclear stopping power. Then there is another terminology note about this term stopping power. The name is somewhat misleading because, as I already said, the electronic stopping is a force. It has units of force. Whereas power in physics, of course, has completely different units from force. Because of this, one of the most leading scientists in this field, Peter Sigmund, he argued in the late 1990s that one should, instead of stopping power, call about discuss about stopping force. And he sort of has a point, but this hasn't very well caught on that it seems that the word stopping power is at least 10 times, maybe 50 times more common than the term stopping force. Also, the word power is not completely stupid here, because if one thinks from an ion point of view, you can think that here the ions is done by a force. But if you think from a material point of view, if you ask the question, how good is a material to stop the ion, then one can talk in English language of the power of a material to stop ions. And this usage is actually consistent with the use stopping power to describe bulletproof vests. If you Google on stopping power or look at stopping power in the scientific literature, you will find that there is also a number of studies how good bulletproof vests are at stopping bullets, which of course, if you are a company developing bulletproof vests, this is obviously the key question you want to know. And this is analogous to how good a material is to stop ions. Although the ions, of course, don't kill people. So anyway, on this course we will stick using to the more dominant term stopping power. And now if you look at these curves, you understand this picture a bit better, because you saw that the electronic stopping dominates at high energies, so this was this regime, but then at the lowest energies the nuclear stopping power dominates, and that's the reason why we have this dense set of collisions here at the end of the ion path. Another interesting and scientifically very important question, which we will mention now, is what is actually the charge state of an ion when it enters the material? This is actually not such an obvious question. When you have an accelerated ion in vacuum, it will have a charge state, and if it's really good vacuum, the charge state won't change, because the ion has this number of electrons and they will stick with the ion until it collides with something. But immediately when it hits a material, it does start colliding, and then the charge state may change. And this actually relates to the ion velocity. So when the velocity is low enough, the regular quantum mechanics of solids applies, and in that case the solid, including the ion in it, has time to reach the electronic ground state while the ion is moving, and in this case it becomes quasi-neutral. That is, it has the charge state as if it wouldn't have any velocity. You can imagine that you shoot an ion in, say a boron atom in silicon, and when it's in this regime, you can imagine that you would stop the ion, remove all its kinetic energy, you would have a boron atom in silicon, then you would calculate what is the electronic distribution around this boron atom. It would most likely be more or less neutral, maybe +1, maybe -1. But anyway, this charge state doesn't have to have any relevance to what the charge state of the ion was when it was shot in. One can put this a bit more scientifically by saying that when the velocity is below the Fermi velocity, which in this graph is roughly somewhere here, below the maximum, when it's below the Fermi velocity, the electrons have time to neutralize. That is, the Born-Oppenheimer approximation of quantum mechanics applies, and then it will have these charge states as if it would be rest. Of course, when the ion enters, it takes a while before it reaches its equilibrium state, because it did have charges, but there is a sub-range of ion beam physics known as hollow atom studies, which has studied this experimentally, and now it's known that this neutralization happens within the first 1 or 2 atomic layers after the ion enters, so it really happens quite quickly at the surface, and after that it's quasi-neutral. So in that case, really the history of the ion atom matters, and then this means that it doesn't matter if it was initially a recoil starting inside the lattice or an ion entering the material. So this means that if you have a high energy particle, any high energy particle, it doesn't have to be an ion. This could be a neutron, gamma, even more exotic particles like muons. So when they hit a recoil, this recoil will produce a damage as if it had been an ion. Or in other words, one can also say that with respect to damage production, one could say that ions, atoms, and recoils are the same thing. And this is actually a great advantage because this means that to understand damage production by ions or atoms, except for surface effects, the physics is exactly the same. So we don't have to simulate these separately, we can just simulate them once and then understand it. So this is definitely good news for our studies. It simplifies life. Well, the other good news is that in metals, excited electrons, and I emphasize the word excited electrons, which are being excited by the electronic stopping, they do almost never produce damage. In ions, ionic materials and organic materials, they may. This is roughly speaking by electrons exciting covalent bonds into antibonding states or exciting ions into a different ionization state, and this may lead to damage. And this, in semiconductors also this covalent bond breaking may lead to damage. But in any case, in metals, one can quite safely say that in almost all cases the damage is produced by the atomic recoils. It doesn't matter if the original particle was an alpha, beta, gamma particle or neutrons, the damage production mechanisms are the same. Usually in semiconductors, like in silicon, this is pretty much the case, although silicon is not quite as simple. And again, in some organic materials, it's quite different. The other opposite extreme is biological materials, where almost all of the time, all damage is from electronic stopping, and the ion collisions don't matter almost at all. But anyway, because of this, we will spend quite a lot of this damage production by atomic recoils in materials, especially in section 5, but also in section 3 and 4. So, from this charge center point of view, this regime, the so-called Bragg peak, it's the maximum the electronic stopping power. Here the charge state issue is very complicated. It turns out that this is known from experimental studies. The charge state actually keeps changing. That is, it has a memory of the previous charge state, but while it travels in the lattice, occasionally it loses electrons, occasionally it can gain electrons. So ions with the exact same energy may have different charge state. And actually this, in that case, this plot is actually simplified, because if it has a different charge state, the electronic stopping will also be somewhat different. So this curve is here understood as an average, whereas individual ions may actually have a different stopping power. And in this regime also, in non-metallic materials, one can have damage production, which we'll return to soon. On the other hand, you see that the nuclear collision cross-section has gone extremely low. So in this regime, there are essentially no nuclear collisions, and all the damage is produced by the ionizations, or there is no damage. Moreover, I told you that the electrons are too light to change the course of the ions. So once one is in this regime and the higher energy regions, then the ions essentially move straight, and if they produce damage in straight tracks. And this is what's known as the Swift-heavy ion regime, which was already mentioned. So in the Swift-heavy ion regime, if an ion comes in, it produces damage in the material. And this animation here will show how a gold ion with an energy deposition or electronic stopping of 5.8 kV per nanometer produces damage in quartz. So you can see that after a quite messy phase, when the material got very hot, one has destroyed the quartz crystal structure and gotten this amorphous regime in here. And these tracks, which are illustrated here, you can see it's in the nanometer scale. This whole cell is only 8 nanometers, so this is roughly 4 nanometer in diameter track here. This can be seen experimentally. So this is an experimental picture of actually a mineral, natural mineral, where the tracks have been made visible after a special etching process in a light microscope. And you see there is a number of tracks here, and these can actually be used to figure out how old the sample is. What happens here is that there is a very small fraction of radioactive isotope with long lifetimes when they which undergo fission. When this radioactive undergoes fission, then one gets this fission recoil, which I mentioned earlier, and this fission recoil will produce damaging the material. We'll get back to this issue of what the mechanisms here are. So if these looked completely incomprehensible to you, you will get some explanations later on in the course. Although it's not fully comprehensible to anybody, it's not fully understood what goes on in this regime. This simulation can reproduce experimental data, but the way the energy is deposited is probably not exactly correct. But the ion tracks, they have a feature, they have a well-defined threshold. That is, they depend on the electronic stopping power, and there is a threshold which almost always is a few kiloelectrovolts per nanometer, and below this threshold energy there is absolutely no ion tracks. So it really relates to high energies, and then there is some limit below which these tracks do not occur anymore. And this is pretty much it for this code. I'll just in the end mention some computer simulation codes which are used to simulate energetic particle penetration. For ions, there are the so-called binary collision approximation codes. These are discussed in big detail in the next section, so know more about them. For neutrons, there are several well-established codes which are maintained by the OECD, Nuclear Energy Agency in Paris. They have a database where OECD member countries can get these codes. There are several neutronics codes like Spectre, Enjoy, MCMP, which can be used to calculate neutron passage in matter. And this is actually a very funny thing. MCNP, it's a code which is still used, which dates back to 1956. Because the Fortran language was the first programming language, was only made in 1957. So this was probably made with some pre-version of Fortran. So this is almost certainly the oldest computer code which exists, which is still in regular use. For protons, there are a different set of codes which can simulate this photon and electron gamma cascade. Probably the most used one is EGS4, which is a modular tool which can be implemented in different geometries, and also Penelopes and other software. And then for radiation transfer at really high energy ions, we're talking hundreds of MeVs, GeVs. Then there are codes which are used for this, especially GANT4 code is used a lot to study radiation detectors in particle accelerators and in space. And these are used at high energies. At very low energies, these are not fully useful anymore. This can be used for many different ions, photons, more exotic particles, and so on. So this was this section, and now I'll again won't read out what you should have learned, but leave it for you to read for a moment here. Thank you for your attention on this set of lectures.